Presenting Hybrid Computational Framework for Fault Detection in Coil-winding Manufacturing Process using Knowledge Distillation. Welcome to the University of Sheffield, located in the UK. Let me introduce you to the Automatic Control and System Engineering Department. At the ACSE department, we're working on multiple projects related to electrical machines. For this research, we're focusing on linear coil winding. In the context of electrical engineering, refers to a method of winding wire onto a core or a bobbin to create a coil, such as the one used in motors, transformers, inductors, and similar devices. This process can be manual or automated. The linear part of the name comes from the fact that the wire is wound in a linear fashion, often along the length of the bobbin. Due to the nature of the copper wire, which is a deformable material, faults tend to occur throughout the process due to the interdependencies between the input parameters and the output parameters. To tackle this problem, an approach to create a hybrid computational framework for fault detection in coil winding was suggested, using the approach of knowledge distillation. A teacher model will be created, in this case a discrete event simulation model, that will be fit into a student model in order to detect faults faster. The DES model is capable of modeling interdependencies in a linear winding process. The DES model simulates a bobbin composed of 5 layers, each with 20 turns. The circles represents the copper wire. A green circle represents a non-faulty wire. Red represents a turn with high electrical resistance. A circle with a letter represents a geometrical fault, such as double winding. The DES model was run using the following input parameters: bobbin shape, wire size, and speed. Multiple bobbin shapes were used for this experiment. Another input parameter that was changed throughout the process was the copper wire. The electrical resistance is calculated per turn, and high electrical resistance is detected. By knowing the position of each turn with high electrical resistance, it's possible to locate hot spots in the windings. The Discrete Event Simulation model outputs a summary of the number of faults and the type. The outcomes are presented in the form of tables. Python was utilized to develop the student model. 3 different sizes of databases were created for either representing of electrical or geometrical faults. The database's size started from 10,000 instances up to 40,000. 6 different supervised machine learning algorithms were compared to determine the fastest and the most accurate model. Results show that random forest performed the best in both cases, reducing the time up to 0.52 seconds per bobbin. The validation process showed that the random forest is accurate at predicting faults.